My name is Wei. I'm one of the senior architects at Baidu working on deep learning, especially enable deep learning on Spark. And I'm together with my colleague Kyle, also from infrastructure team, and a senior researcher from Baidu Institute of Deep Learning. His name is John. So this is a joint work between Baidu infrastructure team and also the Baidu Institute of Deep Learning. So just to get a little bit background on this, like why we need to do this project. So basically, we have a lot of teams in Baidu which like uses Spark for different data processing, which includes like batch processing, stream processing, Spark SQL, and MLlib. So when they try prototyping models in Spark, it's very fast to get things done quickly, and then they can use a very basic models which are already provided by MLlib. But the thing is that when you need to improve the qualities of the model, you need to try a more complicated things such as deep learning. So Baidu already spent a lot of investment in deep learning since 2010. So we had deep learning usage in Baidu across all of the product line, which includes image search, as-CTR prediction, machine translation, and speech recognition. So the main goal here is try to enable users which you already use Spark to seamlessly use deep learning and without minimal code changes. So just want to get some the scales of Baidu in terms of deep learning training data. So for image recognition, we have about 100 million instances of training data. And we also have OCR, speech recognition, and CTR. So just to mention CTR, as-CTR prediction is the largest scale deep learning training instances using Baidu. Not only the training instance is very large, but also the feature size is also across multi-billions. So the number is only captured 2012, and it's starting growing and growing up to now. Since last year, we start to build a product called Baidu Spark 1. The goal of this product is to enhance the overall user experience of using Spark across all teams and to enhance the user experience for different Spark applications. Not only we did a lot of performance improvement, feature improvement based on the current Spark, but one of the big focus is to add deep learning. So we provide a very easy APIs for users in Spark to use deep learning, and underlying that, the library is developed by Baidu Institute of Deep Learning, which is a C++ based training library. It includes trainer and also includes the distributed parameter server support. We also want to address the resource management and also hardware heterogeneity, because we don't want to have two different clusters, one is for deep learning, one is for Spark. So we do resource management for heterogeneous computing hardware, which includes CPU, GPU, and FPGA. So just to recap, the library I mentioned about developed by Institute of Deep Learning is called PADL. PADL stands for Parallel Asynchronous Distributed Deep Learning Library. It supports distributed parameter server to do synchronous and asynchronous parameter update using parameter server, distributed parameter server. Also, in local training, it supports multi-GPU and multi-CPU. And it supports sparse model, not only in local sparse model, but also in remote sparse model. And it provides an easy-to-understand API for user to add new layers. So the API will be very much like Cafe, like it's done in a layer-wise style. And also it supports rich features for deep learning, especially for NLP use cases. I think John will talk about in detail about this software. We also do a little bit of comparison between PADL versus the other popular deep learning stack, which includes Cafe, TensorFlow, and Torch. We feel PADL does a very good job in terms of like distributed training, performance, customization for user, and sparse model support, as well as like integration with Spark. So for Paddle, just to mention, like for sparse model, we realized like TensorFlow and Torch already support sparse model, but their sparse model is only for sparse input. But our sparse model, like developing Paddle, is not only for input, but also for the parameter update. So the performance will be much better. And also for the wide spread of applications, Paddle itself already support NLP, speech, computer vision. So a lot of those already developed in Paddle, using Paddle. And it supports GPU, CPU, and FPGA already. So in order to integrate Paddle on top of Spark, we implement the Spark ML abstractions to let user train deep learning models with minimal code change. So that if you are already like a Spark user, which is familiar with Scalable, we already provide that implementation so it can invoke distributed deep learning training. And we want to have the more complicated scheduling algorithm implemented to do parameter synchronization training in the Spark cluster. And we want to handle the multi-tenancy and heterogeneity. For Spark, MLlib, it already supports hyperparameter selection. We also add a more rich feature, hyperparameter selection, so that when user train models, it can fine-tuning based on the different hyperparameters. And for batch and streaming learning, we basically want to initially Paddle mostly supports batch learning, but we want to implement online learning using Spark streaming. So basically, Kyle will cover about some of the design details for enabling Paddle in Spark. So next, I'll give it to Kyle.
My name is Kyle. I will talk about the high-level design concept and the design decision we did when we try to integrate the powerful deep learning platform called Paddle into Spark. And as this picture, you can see the four main components involved in this project. The underbutton tool is covered inside the Paddle, but I pull out the parameter server as one important component, although it's also included inside the Paddle. The parameter server here is a distributed one, and it takes care of the parameter synchronization in really high efficiency and performance. And the detail will be covered by the last Paddle developer, John. And Spark and Yang on top of that, Spark will take care of the training environment setup, like all the training input preparation, and after the training finish, the model serving will be taken care of by the Spark. And Yang will do a resource management. As you see, when try to support multi-tenancy and heterogeneous the CPU and GPU inside a training job. And here, I'm trying to tell about the data flow, for how we pipe the data from Spark into the Paddle deep learning platform. You can see on the right-hand side, the blue box is actually the Paddle component called data provider. And it's also sharded and partitioned. And on the left-hand side, each one is, you can say, a data frame partition. When you actually wrap the raw training input data inside data frame, the data source could be a DB platform, the DB table, or it could be a plain HDFS file. And wrap it in the data frame and do the partition based on the size of the trainer that when putting in the config of the Paddle deep learning. And then writing through each Spark executor to each Paddle trainer through RPC. So basically, the only interface from Spark to a deep learning platform is the RPC interface. And I'll explain why we didn't change much inside Paddle. And here, give you guys a high-level system architecture overview. On the bottom is a YAM cluster. All the resource management is held by YAM. It supports GPU and CPU. And in here, you will see there is a one-to-one mapping from Spark executor to a pedal channel. And it actually is different. Like when the project actually got some inspiration from Cafe on Spark, but when take a different design choice, when keep the deep learning itself inside a black box, because we think the parameter synchronization and the training scheduling inside deep learning is heavily tuned. When we involve the pedal scheduling in it, or when we put the training process inside a Spark executor, it will not improve the performance, it will not speed up the training. So we actually keep pedal trainer and Spark executor separate. And this one also just shows an ideal case that YAM could allocate the Spark executor to a pedal trainer in the same partition into the same machine. But it doesn't have to be the case. It could be some case that when do the data preparation inside a CPU machine, and then when process do the training in the GPU machine, then it won't be the same node. And also inside the Spark driver, we do the same thing that Spark context used to manage the Spark executor. When implement a pedal context to manage all the training configs and training the status. And there's a main function pedal algorithm to coordinate these two. And from here, I will talk about the API design. As Wes mentioned earlier, we try to provide a seamless support for deep learning in Baidu. So we encapsulate pedal inside a Spark ML abstraction. This shows the Spark ML abstraction. It will be an estimator for the train part and the predictor for the model prediction part. And I will show some code snippet how we encapsulate these two. Oh, and to support deep learning inside Spark ML is not, there are some missing pieces. Like the current Spark ML parameter abstraction doesn't cover the neural network parameter sets. You can see here, inside a neural network or deep learning training, normally it will involve the convolution layers, pooling layers, full connection layers. All layers has their own configuration. The current Spark ML parameter abstraction doesn't have it. So when add the neural network parameter inside. And here is a code snippet that shows how we extend the pedal, the Baidu's deep learning platform as a Spark ML estimator. So you'll see the pedal classifier is actually extended predictor. Predictor is actually extended class from estimator. And after the training, it produces a pedal classifier model, which is normally a subtype of a model. And a pedal classifier model is extended by the pedal model. So when you use it, you will just like the normal Spark ML Spark ML machine learning class, just do classifier.chain and the model.predict. It will just like this. Also, we want to emphasize one of the design decisions we did here. Instead of do a lot of task configuration, we try to call your configuration, because a deep learning configuration involving a lot of layers and a lot of parameters. And normally, people wants to do hyperparameter, wants to speed up the trainings, trigger a lot of trainings with different configuration at the same time and figure out the best configuration. And when instead of doing the test space, you put a lot of test file of configurations when do the coding to code your configuration. And here is an example of other way that the cafe, it will shows a lot of layers. And when some of the scientists in Baidu, they are using cafe to training, they normally will make the problem that there are some typos inside the long text file. There are some wrong setups inside the text file, but it only has to trigger the training to figure out. But with the code level, the compiler and a lot of sanity check could be help to prevent this. And here I will conclude the design decision we have here. So we think it's more important to make this deep learning support inside Spark compatible to Spark ML. Then we implement some deep learning scheduling under Spark. And another big point is when do the code level configuration instead of the test level configuration, because it's easier and it provides more flexibility when you can call your own rule. Like different layers have their dependency rules. You can call it and trigger the training. Then it will spawn all the training instances you need and conclude the best one for you. And next one is the internal detail about the pedal itself, how when thing is good is better, and John will talk about it. Do this, John.
Hey, hello everyone. I'm John. I'm going to give you a brief introduction of the design of Pedal. So Pedal is designed to be a general purpose and highly scalable architecture at Baidu for deep learning. So for input, it supports all kinds of input like image, text, and speech. And then it distributes the input to trainer, which computes the gradient for neural networks. And the trainer supports CPU, GPU, and FPGA if they're available. And after it computes the gradient, it sends the gradient to parameter server. And then parameter server supports different kinds of algorithms to reduce parameters. For example, we support synchronous stochastic gradient descent and asynchronous stochastic gradient descent, and also batch method like LBFS. And then we also support different kinds of neural networks. We support recurrent neural networks for sequence data, and we support convolutional neural networks for image data, and also support high-dimensional sparse fully connected neural networks for high-dimensional data. And users can combine all of these kinds of neural networks together and train a very large model in an end-to-end way. So first, let's describe the design of parameter server for Pedal. So for Pedal, usually we have a trainer and the parameter server co-locate together. So usually when there's one trainer, the parameter server resides on the same machine. And also for the parameter server, the parameters are sharded across the parameter servers, but it's not replicated. And also this has all-to-all communication between all the parameter servers. So the design of this parameter server architecture is because our very special hardware at Baidu. So at Baidu, we usually use GPU to train our models because we find GPU is much faster than CPU when training deep learning models. And we usually have 4 GPUs per machine, and usually we have 4 to 10 machines. And we find this size of machines are enough for our data size. And all machines are in a single high-performance switch, so that the peer-to-peer communication bandwidth are the same for all types of parameter servers. And this is the reason why we use all-to-all peer-to-peer communication. And then we also have a fairly reliable data center. And we find in our data center, there are very, very few failures. So we don't do any parameter replication. And because we highly focus on using GPU, we use a very special synchronization scheme for GPU. So it's called ring synchronization. So basically, what it means that when we have some GPUs, we arrange the GPUs in a ring. For example, if we have 4 GPUs, so the 4 GPUs contain a ring. And we choose this architecture because of the topology of the GPU hardware. Usually, for example, if we have 2 cards, and each card has 2 GPUs, and the bandwidth between the GPUs on the same card is much larger than bandwidth of the GPUs in different cards. So this is the reason why we choose to use the ring structure. For all the parameters, we only use one GPU as the main GPU for the parameter, and this GPU is responsible for reduce the parameters gradient from all the GPUs, and then it's also want to scatter the reduced parameter to all the GPUs. And if we use the ring structure, you can say that because the communication only happens in the ring, so that for each parameters, the parameter only goes through the slow and low bandwidth connection 2 times, one for reduce and another for scatter. And if we use a fully connected and peer-to-peer communication, one parameter should go through the slow connection about 3 times or 6 times, depending on the implementation. And so our implementation is much more efficient when there's slow connections. And when there's a slow connection in the network, for example, if we have different groups of networks that connected by some routers, we can also use this kind of architectures. And this is our experiment on the scaling performance. And so this is we train Alex on a number of machines with 4 GPUs on each machine. And we have 2 types of network architecture. So we can use TCP, and we also use RDMA, which is a much faster protocol for high-performance computing. And we can say that if we use RDMA, we can achieve linear scalability in up to 5 machines. And we also can achieve linear scalability if we have more. Okay. Okay. Another important characteristic of Baidu is sparse training, because in internet company, especially for advertising, the features can be very large. For example, for advertising, it can have billion features with billions of dimensions. But for these features, usually the features are very sparse. For example, in one data, usually only a very tiny fraction of the data are non-zero. So we want to employ this special property of data to make our training more efficient. So we call this sparse training. For sparse training, for example, if we have a sparse feature vector, so we should have a dense parameter matrix. And this dense parameter matrix is stored on parameter machine. And in each data batch, because in each batch only a very little fraction of data is non-sparse or non-zero. So we only need to fetch the fraction of data parameters from parameter server, and we only need to update this fraction of parameters and send it back to the parameter server. So in that case, both the communication and computation are much more efficient than dense training. And this is our experiment on compare sparse training and non-sparse training. And the blue curve is non-sparse training, and the purple curve is sparse training. And for this data, we have 115,000 dimensional feature, and usually only about 1% or 2% of these features are non-zero. And you can say that when using sparse, our training is much more efficient. If you're non-sparse and in one machine, it takes about over 200 seconds for one batch. But if we use sparse training, it only takes 1/10 of the time. Okay, and another important implementation is our flexible and efficient RNN implementation. So RNN means recurrent neural network, and recurrent neural network is very good for sequence data, and recently it has been used for speech and natural language processing. But one challenge of recurrent neural network is that because it handles sequence data, you need to go through the time steps for each sequence in a sequential way. And how to do batching for sequential data is very challenging. And for TensorFlow, they usually use something called padding. So basically what they do is they pad the data to same length so that it can be processed in a batch way. But we found that this is highly inefficient because, for example, if we take example of this data, for this data, the first sequence has 3 time steps, the second has 2 time steps, and the third has 1 time step. If we pad data, we need to process 9 time steps, right? But if we don't pad it, we only need to handle 6 time steps. And what we did is we first had a scatter operation to reorder the sequence so that the first time step of each sequence is together, and the second time step of each sequence, if there is together, and the third time step of each sequence is together. And then we do recurrent neural network for each time step sequentially, but in a batch way. And then we gather the result together, and then we get the output. And we find this implementation is much efficient than TensorFlow. And you can see that we compare a machine translation task with batch size of 64, and embedding size of variant size, and dictionary size of 10,000. And we find our implementation takes only about 1/2 of the time of TensorFlow because of our clever non-padding method used. So because of our architecture, we also train a very large-scale machine translation model. So this machine translation model is trained on 8 machines, and each machine with 4 K40 GPUs. And we have 9 RNN layers for encoding, and 7 RN layers for decoding. And word embedding size is 286, and RN size is 512. And our byte size is 25,000 characters. And when train our models on our data platforms, if we use attention for 100 batch, we take 25 minutes. But if we don't use attention, just encode the decoder model, we only need 90 minutes for 100 batch. That is a very fast speed for the model that of this scale. Okay. And for the next step, we also want to support stream training. So stream training basically means when some data get together, we update the model in a streaming way so that the model can reflect online. This is very important for our application of advertising and also news applications. Okay, thank you, and I'm ready to take questions.
So thanks very much for this awesome presentation. If we've got about 4 minutes left for questions, if you do, please go to the microphone and ask away.
Hi, this is Andy Fan working for the Cafe on Spark. So anyway, I have a question for you. And when you talk on the parameter server, do you use the CPUs or using GPUs? And then how does the communication is happening between the training process and the parameter process?
So the question is that whether the parameter server is on GPU or on CPU. So usually our training process, like the trainer, which computes gradient, is on GPU, but the parameter server is on CPU. Because in this way, first we use both CPU and GPU for our training, and also for compute gradient, using GPU is much faster because it needs at least lots of matrix modifications. But for parameter server, it basically what it does is just sum the gradient together, which is not very efficient on GPU.
And then my second question is, when you have multiple trainers, is this the update of the parameter server is synchronized or asynchronous?
Usually the question is that whether we use synchronous or asynchronous update for parameter server when we have a large number of trainers. So previously we used asynchronous stochastic gradient, but recently we find that even for very large number of trainers, for example, like 100 trainers, using synchronous stochastic gradient usually result faster result if we can choose to discard some fraction of the gradient. So basically, right now, almost all of our job use synchronous stochastic gradient.
Thank you.
Hello, thank you for the very awesome presentation. I have questions about how do you transfer data from Spark to Paddle?
Actually, we open RPC interface from Spark, from Paddle, and each trainer and executor is a one-to-one mapping. So each executor will write through the RPC interface into Paddle trainer.
All right, so just to confirm, so the Paddle process will just wait for new data coming from Spark, or how is it going to be?
I didn't quite get your...
Oh yeah, I mean the question is the trainer in Paddle just wait for the new data from Spark, or...
Yeah, there is a data provider process is a multi-thread that server. It will waiting for, it has a buffer to wait for the RPC.
Okay.
Yeah.
Do you write it to any storage or just totally in memory?
It's totally in memory or the data provided part.
Right now only in memory.
Yeah, in memory. Yeah.
Okay, thank you.
Thank you.
Two quick questions. Does the parameter server talk among themselves?
Yes. Let me see. That depends on the implementation. So usually, I think that usually they don't. Our question is that whether parameter server talk to themselves. Usually they don't. So usually only trainer talk to parameter servers, and yeah, no.
How do you handle parameter server failure?
So right now we don't handle that. We don't handle parameter server failure because we have a fairly reliable data center, and it's happened very rarely in our data center.
Well, you could have a training job last 2 weeks, right? Like, it's possible some parameter server is going to fail, right?
Yeah. But right now we haven't been implemented the method to handle that. But actually we can handle that even because right now we have mechanisms. So the mechanism is that so we can discard some very slow parameters. So, oh no, we can't handle that. We also need some like the verification. No, basically right now we can't handle that. This is our future work.
I see. You also don't handle
Sorry,
stragglers.
we're going to have to shut it down just because we're going to switch. But you can always ask the questions afterwards. So I want to thank very much for our speakers, and that's it for now.